with 2 pi period. Happy New Year. So this is the last part about infinite series, about infinite summation. Okay, this lecture is about a special series called Fourier series. Okay. So we will discuss about general Fourier series for periodic functions and special Fourier series for odd and even functions, and also convergence of Fourier series. So let's go through this quickly today. If we have sufficient time, we will also discuss some exercise questions. So what's Fourier series? Fourier is a French mathematician. He's a person, and he is also a physicist. He found that if a function is periodic with 2 pi period, then the function can be viewed as a composition of some trigonometric functions. So what are trigonometric functions? They are cosine functions and sine functions. These functions are called trigonometric functions. Okay. So Fourier found that if a function is 2 pi periodic, which means that if this capital T is 2 pi, if you add a variable to 2 pi, then this doesn't change the function value. So ft plus 2 pi is always equal to ft. Such function is called 2 pi periodic. So he found that 2 pi periodic functions are always a series of cosine and sine functions. Okay, so they are equal. So therefore, later this type of a series is named as Fourier series. Okay. So in this series, A0, An, Bn are just numbers. They are called Fourier coefficients of the function. So if a function has such a Fourier coefficient, then these are A and Bn are just the Fourier coefficients of this function. Okay. So a function is uniquely determined by its Fourier coefficients. Okay. So why people study Fourier series? Why people study series consisting of trigonometric functions? Because trigonometric functions are very special. They have very special properties like orthogonality. Okay. So orthogonality means that if you consider two different trigonometric functions, and consider the integral of their product, then this will be 0. So the integral of the product of any two different trigonometric functions is 0. So if they are different, then their integral is 0. So if they are the same, then the integral may not be 0. For example, so if cosine nt times cosine mt, if you compute the integral, then if they are different, then the integral would be 0. So what do we mean different? If n is not equal to m, then these are different cosine functions. Okay? If you compute the integral of two different cosine functions over the interval from negative pi to positive pi, then the integral of this would be 0 if they are different cosine functions. If they are the same cosine function, then you are computing integral of cosine square nt, right? If you compute the integral of cosine square, a square function is always positive. So the integral would not be 0, it would be pi if n equals m. So when you consider the integral of the product of the same cosine function, then it's equal to pi. The same holds for sine function. If they are different sine function, then the integral would be 0. If they are the same sine function, the integral would be pi. Okay. So these are called orthogonality because different functions, different cosine functions, and different sine functions are orthogonal. Orthogonal about the integral. So the first identity tells us that cosine function and sine functions are orthogonal to constant, because this can be viewed as constant times cosine function and constant times sine function. Okay, so the integral of this product is 0 means that the constant is orthogonal to cosine function. Constant is also orthogonal to sine function. Okay. These are orthogonality properties, and they are especially useful in determining the Fourier coefficient of the function. So we will talk about this later. Let's temporarily remember this special orthogonality property. Cosine and sine functions have many useful identities called trigonometric identities. There are many of such identities. You can find this in Wikipedia, okay, or you can just look for these formulas here in the lecture note or in Wikipedia when you are when you try to work out a problem. Okay. So let's briefly present the proof of this orthogonality. This proof uses trigonometric identity. So it uses this identity. Okay. If you consider the product of a cosine and sine function, it can be converted to a sum or difference, either sum or difference. Okay. So the product of any two trigonometric functions can be converted to a sum or difference. Okay. Well, here on the right side, each term does not contain product. It's just a single trigonometric function. So we will use this. So here, the product of cosine and sine function can be converted to a difference. Okay. And it can be converted to sine function minus sine function. Here, if the number here, frequency here would be n plus m times t. Here would be n minus m times t. So this is the trigonometric identity here, the fourth row. Okay, so we use this property here. So after we convert the product into a function without product, you can integrate this sine function easily, right? The antiderivative of the sine function would be cosine function minus this. So this antiderivative of the sine function would be cosine function, and minus 1 disappear. So then you substitute t to be pi or negative pi, you would get the answer. Okay, this would tell you that if n is different from m, if there are different numbers, then you would get 0 because here, if n is different from m, you get n minus m here and minus n minus m here. Cosine function is an even function, so this minus sign can be eliminated. So this blue part would be 0. Okay, this black part would also be 0 because you can remove this minus. Okay, so if n is different from m, you can get this. Okay, what happens if n is equal to m? If n is equal to m, you cannot integrate the sine function here because you would get n minus m in the denominator. This cannot be 0. Okay, so if n is equal to m, you simply don't have this term. So this term disappears. You don't have this blue part. Okay. So in that case, if you don't have this blue part, you only have this black part. Then the integral hold on. So if n is equal to m, then this integral is still 0 because black part is still 0. Okay, so this doesn't matter. So even if you don't have blue part, the black part is still 0. So this shows the orthogonality of this function. When n equals m, you simply don't have blue part, but it's still 0. Okay. This is cosine function times sine function. Okay. For cosine function times cosine function, you can prove it similarly. Okay. When n is not equal to m, you can integrate this cosine function. You would get n minus m in the denominator. Okay. So you would get 0 in the end. But when n is equal to m, you wouldn't have this part. Okay? When n is equal to m, you cannot have 0 in the denominator. What you have is cosine 0t here. Cosine 0t always equals 1. So if you integrate 1, what do you have? if this number is 1 here, if you integrate 1, you get 2 pi, right? 2 pi divided by 2, you get a pi actually. So integral of constant is just the length of the interval, 2 pi divided by this 2, you get a pi. So this shows you why you get a different result when n equals m, because you get a 1 here. Okay, if you integrate 1, you get a non-zero constant. Well, if it is not 0, then you would get this blue part, and the blue part would be 0. So this shows the orthogonality between different cosine functions. So all of this depends on the trigonometric identity we use here. Okay, you can find this formula in the lecture notes anyway. You don't really need to remember this. Of course, remembering this will help you to solve problems quicker. Okay, so as an exercise, I would recommend you to verify this identity after class by yourself. You verify the orthogonality between different sine functions. If n is different from m, you get 0. If n is the same as m, you get a pi. Okay? This is very similar as this orthogonality between cosine functions. Now you can verify this by using different trigonometric identity for sine function. So this is an exercise for you. So those orthogonality conditions, which are easy to prove but have very important applications, they are very useful. They are especially useful to find the coefficient of a given function. If you are given a function f, then how to determine this coefficient in its Fourier series? Just use the orthogonality. For example, you just integrate this function over the interval. If you integrate it on the right-hand side, you would have the integral of 3 parts. Integral of the first part, constant part, integral of the cosine part, and integral of the sine part. Well, you only have this first part left because integral of a cosine function is just 0. Integral of sine function on the standard 2 pi interval is also 0. So the second term and third term would be 0. And integral of constant is simply this constant times 2 pi. So 2 pi divided by 2 would be pi. You get A0 times pi. Okay. So why do we have this 2 here in the denominator of the constant part? Because we want to have pi here instead of 2 pi. Okay. If we don't have this 2 in the denominator, we would have 2 pi times A0. So in order to make this formula the same as the formula for an, we would divide A0 by 2 in the constant part. Okay. Later you will see the formula for an is also involving pi. Okay. So the first constant part, A0, equals the integral of the function divided by pi, because you can divide pi on both sides, right? On the left side is this integral, right side is A0 pi. You divide pi on both sides, you get 1 over pi times the integral for A0. So this is how we determine the constant part, A0. We simply integrate the function and all the cosine and sine parts disappear. We get A0, right? So if we use this idea, we can also get an and bn. The method to get an is integrate the equation against cosine mt instead of constant. We multiply the equation by cosine mt and then do the integral. This time, the first part would disappear because this is integral of cosine function. Right? Integral of cosine function over the standard interval would be 0. The third part would be 0 because these are integral of sine and cosine functions. They are different, right? The different trigonometric functions are orthogonal to each other. So this integral would be 0. Okay? So only the second part contains non-zero term. Okay. So if n is different from m, then it's 0 because they are different cosine functions are orthogonal. So in only one case, it's not 0. So in the case that n is equal to m, so you have infinitely terms. You have infinitely many terms, but all of the terms would be 0 except one term when n equals m. So you only pick up that one term, that's integral of cosine m squared, mt squared. So integral of cosine squared would be pi, right? That's our fixed result. So you would get pi times am. Recall that when n equals m, you get am times cosine mt squared. Well, the integral of this cosine square would be pi. So you get am times pi. So what's am? Dividing pi on both sides. Am would be this integral divided by pi. Okay, this is the same formula as a0. So a0, recall that a0 is the integral of the function over pi. Am is the integral of the function against the cosine function over pi. Okay. So integral of the function can be regarded as f times cosine 0t. Okay. If you look at the previous page, a0 is ft times cosine 0t. Then with the integral, cosine 0t is just 1, right? So this is the same formula as am. Okay. So we get a formula for am in this way by using orthogonality between sine function and cosine functions and orthogonality between different cosine functions. We can get am. Well, similarly, you can also get a formula for Bn. Okay. Well, you can immediately imagine that if you want to get Bn, you should multiply this equation by sine function and then compute the integral, right? So that's completely similar. We integrate this against the sine function, against the sine mt. So this should be sine mt. Okay. If you integrate this against the sine mt, the first term times sine mt, the integral would be 0. For the second term, cosine function times sine function, their integral would be 0, because the cosine function and sine functions are different trigonometric functions. They are orthogonal. So their integral of their product is 0. Okay. So for the integral of the product of sine functions, so there are infinitely many terms, right? When n starts from 1 up to infinity, there are infinitely many terms, but all terms are 0 except one term, except when n equals m. If n is different from m, then all of the terms will be 0. Only one term is not 0. That term corresponds to the case that n equals m. Okay. So when n equals m, you have bm here times sine mt squared. Well, integral of sine squared would be pi. You get bm times pi. Okay. Dividing pi on both sides, you get a formula for bm. So bm would be the left side, the integral divided by pi. Okay. So you see that bm equals the integral of the function f times sine f, sine mt. So these are formulas for the coefficient of a given function. To summarize, we have the three formulas. So if the function f of t has the Fourier series, okay, with Fourier coefficients a0, a, and bn, then these Fourier coefficients can be determined by the integral of f. Okay. So in order to compute the coefficient, you should compute the integral of the function. So you may wonder, why do we want to compute the Fourier series of a given function? Actually, Fourier series are the one way that people send signal. So you know that the television can receive signal and to display figures, right? You can watch television. So why? Because the television receives signals. After it receives the signal, it translates the signal into figures, into graphs, so you can see it. Okay. So what signal does the television receive? Just these numbers. Okay. How to transform a function into a television? Because the graph you see are just a graph of functions, but you cannot just transfer a function into a television, right? What you transfer to the television are signals consisting of these numbers. Okay. So you send the Fourier coefficient, these numbers, to the television. And according to these numbers, the television will reconstruct the graph of the function. So you see the television, right? You see the graph. That's one way people send signals. So if you can decompose any function into Fourier series, you can send these numbers as signals to devices that you can make use of it. Okay, so we have three formulas here. For given function f, we know how to compute its Fourier series. Just compute the integral. Let's look at practical examples. For example, let's find the Fourier series of this function. So this is a discontinuous function. It equals -1 when t is smaller than 0, when t is negative. But it equals +1 when t is positive. So the graph of this function is like this. So if this is pi, this is -pi, then when t is bigger than 0, the function is +1. When t is smaller than 0, the function is -1. Okay. So this is the graph of the function. The blue line is the graph of the function. Okay. So if you look at 0, when t is equal to 0, the function equals +1 instead of the -1. Okay. So the function does not take value when t equals 0, it takes value in the upper side as +1. So this is the graph of the function. Well, what's the Fourier coefficient of the function? According to our formula in the previous page, the Fourier coefficient an equals this. So what's an? An equals the integral of f times cosine function. Well, how to compute the integral if f is defined piecewisely? You should split the integral into two parts. The two parts, one part is when t is smaller than 0. The other part is when t is bigger than 0. Okay? So when t is smaller than 0, the function equals -1 as shown here. So here, the function f of t is -1 when t is between -pi and 0. So when t is smaller than 0. Okay, this is the definition of the function. In this case, f of t is -1. But when t is bigger than 0, between 0 and pi, as shown here, the f of t is just a +1. So you need to split the integral into two parts. On different parts, f has different expressions. You use the expressions for each part here and there. And then you can compute the first integral and second integral separately. So after you compute it, you would see that the integral of the first integral is just a sine function. Antiderivative of cosine function is sine function, right? Okay. So sine function, sine 0 is 0, sine pi n pi is also 0. So the first term is 0, second term is also 0. In the end, you get 0. Both terms are 0. So you get 0. So an equals 0. Okay. You don't have cosine series part. You only have sine series part. See, the coefficient of sine series is Bn, which equals the integral over pi of the function f times sine t. So this is our formula. And we also split it into two parts. See, when t is smaller than 0, so this whole interval consists of two parts. Okay, from negative pi to 0, and then from 0 to positive pi. But in the first part, when t is smaller than 0, the function is negative 1. On the second part, when t is bigger than 0, the function is positive 1. So you substitute the expressions of the function into the two parts respectively. This time, the integral is not 0, because if you compute the integral of a sine function, you get a cosine function, right? So cosine, this would be cosine nt over n. The antiderivative of this function would be cosine nt over n. And then you compute the two endpoint values. So cosine 0 would be 1. Cosine n pi would be negative 1 to power n. So in the end, you get 1 minus negative 1 to power n over n. And then divided by this pi here. So that's why you have a pi in the denominator. You have a pi here. So since you have two terms, you have a 2 here. Every term equals this number. So you have two terms. That's why you have this 2 here. So this is coefficient Bn. So coefficient an is 0, so you don't have this cosine part. And you can check that you don't have this A0. A0 is also 0. So in the end, you only have sine parts. Bn is this number. So this is your Bn. So this very complicated discontinuous function can be expressed as the infinite summation of sine functions. Okay. So they are equal, except at the discontinuous point. So they are equal at almost all points except at 0, because at 0, the function is discontinuous. Okay. So this is the first example to find the Fourier series for the function. You just substitute the formula, substitute the expression into the formula here. But when the expression is defined piecewisely, you should split the integral into two parts and use different formula on different piece. Okay. Well, this is our second example. The function is different. Now, when t is smaller than 0, function becomes 1. When t is bigger than 0, the function becomes 3. So this is different from the previous question. Previous question, function value is negative 1 and 1. Here it's 1 and 3. They're different. But if you are clever, you can observe that this function is equal to 2 plus the previous function, the function in the previous question. Okay, recall that the function g in the previous question is defined in this way. Negative 1 and positive 1, right? If you add 2 to this function, you get 1 and 3. That's exactly this function. Okay. So f of t equals 2 plus g of t. And in the previous question, we already found the Fourier series for this g of t. We already found it. Okay. So for this function, we can just add 2 here. So this is the constant part. You still don't have cosine series part. But you have constant part, okay? You have constant part plus sine functions. Okay, so this is one way that we avoid computing the coefficients again, because if you compute the coefficient of the function g of t, you just replicate the previous question. Okay, you just copy the answer of the previous question here. Okay? You don't need to do that. because it's already done in the previous question. You can directly write down the results. You add it by 2. Okay. Okay, let's proceed. Now let's consider a slightly different function, the absolute value of t. Okay? And for this function, the Fourier coefficients again should be found by using this formula, standard formula. A0 is just the integral of the function over pi, right? We have this formula. But what is this function f of t? It's absolute value of t, right? But what is the integral of absolute value of t? The absolute value of t actually is defined piecewise. Okay. It is negative t when t is smaller than 0, and positive t when t is bigger than 0. The absolute value of t should be defined piecewise. It has different expressions for different t. Okay. So we need to split the integral into 2 parts. One part when t is smaller than 0, so absolute value of t in this case is just a negative t. And the other part, t is bigger than 0, so absolute value of t is just a t here in this case. So you compute the 2 integral, you would get your answer. Okay? Every integral equals half pi. The sum of the 2 parts would give you just 1 pi. Okay. Similarly, if you compute the integral of absolute value of t times cosine function, you should also split it into 2 parts. Okay. In the first part, the integral is from negative pi to 0. In the second part, the integral is from 0 to positive pi. Anyway, on the first part, t is smaller than 0 because t is between negative pi and 0. T is smaller than 0. In this case, absolute value of t is negative t. While in the second case, when t is bigger than 0, absolute value of t is equal to t itself. Okay? So you can compute the 2 integrals respectively. Every integral would equal to this number without this 2. Okay? Every integral equals the number without 2. But you have 2 parts. You sum up the 2 parts, you get a factor 2 here. Okay. So this requires you to compute t times cosine t, integral of this function. So let's leave this. Computing this integral is difficult, slightly more difficult. Let's leave this to the next page. Okay. So let's first discuss how to determine the coefficient Bn. Okay. So actually, the computation of Bn is similar. You should split the integral into 2 parts. When t is smaller than 0 and when t is bigger than 0. In the first case, t absolute value of t is just negative t. In the second case, absolute value of t is just t itself, when t is bigger than 0. So the integral of the 2 parts would have negative sign, actually, because t times sine function is just an even function. Okay. If you have an even function, you compute the integral on the 2 interval which are symmetric about the origin, you would get the same answer. Okay, but you have an addition of negative sign here. So actually, with this negative sign, the 2 integral have the same absolute value, but with different sign, with opposite sign. So their sum would be 0. Okay, so you don't really need to compute this integral because they have different sign, but the same absolute value. Their sum is just 0. What you really need to compute is this integral t times cosine nt. So anyway, you get the coefficients. A0 is pi, an is this number, bn is just 0. So you can substitute this coefficient into the Fourier series. What you get is a0 over 2 as the constant part. So you get pi over 2 as the constant part. And an times cosine nt, we sum up all the n. So this is the Fourier series. You can also further simplify it because you see that when n is an even number, this is actually 0 because even power of -1 is just a +1. So you get 1 minus 1, which is 0 when n is an even number. Okay? So actually, when n is even number, you don't have this term because this term is 0. This term is not 0 only when n is an odd number. For example, when n is 2n minus 1. So 2n minus 1 is the odd number, right? When n is an odd number, you get a 2 here. 2 times 2 is 4. So you get 4 over this odd number square times pi. So you are left with only cosine series corresponding to odd number here. Okay. For even number here, the series will be 0. The term will be 0. So this is an example for computing the Fourier series, again for a function which is piecewisely defined because absolute value of t doesn't have a uniform expression. Okay. It's also piecewisely defined, depending on whether t is positive or negative. For all such questions, you need to split the integral into 2 parts and use different expressions on each integral. So we still haven't discussed about how to compute the integral. Okay, in the previous page, we directly give you the result of this integral. The result would be this. But the computation of the integral indeed is not so obvious. I will show you how to compute the integral. And you should remember this because this is a very typical example. Okay? There are many similar integrals to be computed. So if you want to compute integral of a trigonometric function times the polynomial, you should use the integration by parts. For example, you should integrate first the cosine part. If you integrate the cosine part to the right side of the differential operator dt here, so antiderivative of cosine nt would become sine nt, right? So differential of sine nt is cosine nt times dt, right? This is our formula because derivative of sine nt is n times cosine nt. This is what you know. Well, if you multiply dt on both parts, you get this term. So cosine nt times dt is this differential of sine nt divided by n. So anyway, you move cosine function to the right side of the differential operator. It becomes sine function, sine nt over n. And then you use an integration by parts. By using integration by parts, this integral is equal to the product of this term times sine nt minus an integral in which you switch these two terms. Sine nt becomes here, nt becomes on the right side of the differential operator, but n is just a constant, so you can move the constant here on the left side of the differential operator. Okay. So what you need to compute is the new integral with only sine function without t here. Okay. There is no t in this integral. Okay. This trigonometric function is not multiplied by polynomial now. This is the advantage of using integration by parts. You decrease the power of t here because this becomes t to the power 0 here. Power on t decreased. Now the first term is easy to compute. Sine pi, sine n pi is 0, sine 0 is 0. The first term is 0. The second integral is also easy because antiderivative of sine function is just a cosine function over n, over another n. So you get n squared. So what you get is this. So cosine n pi minus cosine n0. Okay. So cosine n pi is negative 1 to the power n. Cosine 0 is just a positive 1. Okay. So this is a standard way to compute the integral of cosine function times polynomial. You should use integration by parts to reduce the power on t. When there is no power on t, you get an integral of a trigonometric function. This is the standard one, standard integral, which you should be able to compute. Okay. So that's the first part of this lecture. So now you know how to compute the Fourier coefficients of a given function. We just compute some integrals where the formula you know already. But there are also some very special functions called odd function and even function. Okay? So what are odd functions? Odd functions are those functions that you can extract this negative sign outside of the function. Okay? If f minus t always equals minus ft, then the function is called odd function. Okay. When ft is such an odd function, ft times cosine nt would be odd function, while ft times sine nt would be an even function. Okay. Because odd function times odd function is even function. Odd function times even function is again still odd function. So consequently, ft times cosine nt is odd function. Integral of odd function would be 0. So odd function is symmetric about the origin. Like this. It's symmetric about the origin for odd function. If it's symmetric about the origin, the integral from negative pi to positive pi would be 0. Because integral on the left part is negative, while integral on the right part is positive. The sum of negative and the positive parts are just 0. Okay? So integral of odd function is 0 on the standard interval, because the interval is symmetric about 0. The integral on the left side would cancel the integral on the right side for odd function. While for even function, it's different. For even function, this is an even function. For even function, its graph is symmetric about the vertical axis. So this is the graph of an even function. For even function, its graph is symmetric about the vertical axis. So So the integral on the left part is equal to the integral on the right part. Actually, integral here on the left side is equal to the integral on the right part. So they are equal. So the sum of the two parts will be equal to twice of one part. So if you integrate this function on the whole interval, it's equivalent to computing the integral on half of the interval from 0 to pi. Only integrate from 0 to pi, only integrate on half interval, and then multiply this by 2. Okay. So this is a coefficient of Bn. You only need to compute integral from 0 to pi, which is simpler, easier. Okay. The smaller the interval, the easier the computation. So to conclude, for odd function, there is only sine series, okay? Because an is always equal to 0 for odd function. You don't have cosine series. Okay? Odd function is always a combination of sine functions without cosine functions. Because cosine functions are even. Sine functions are odd functions. Okay? So odd function should be expressed by using odd function only. So there is no cosine series. The integral here is 0. So this is for odd function. Odd function can be expressed as sine series. While for even function, it should be expressed as cosine series. So what's even function? So you should know this, that even function is such function that f minus t always equals ft. You can remove the negative sign. Okay. For even functions, even function times even function is even function, or even function times odd function is odd function. Consequently, if this is an even function, then computing this integral over the whole interval is equal to computing the integral in half interval, multiply this by 2. While integral of odd function is just a 0. So to conclude, Bn is 0, but there is no sine series. There is only cosine series. Okay, An is not 0. You should compute An in this way, while there is no sine series, no Bn. Okay, this is for even function. Even function should be a combination of cosine series, because cosine functions are even functions. So let's look at this question again. We have considered this question before, right? So this is the absolute value of t. In the previous example, we computed the integral of t on two parts separately, but not actually we can use the property that it's an even function. So absolute value of t is even function because you can always remove the negative sign, right? So it's an even function. So for even function, if you compute the coefficient, you can only compute on half interval from 0 to pi. Multiply this by 2. Okay. So integral of this is easy to compute. It's equal to half t squared. Half t squared when t equals pi is half pi squared. Half pi squared divided by pi is half pi. multiplied by 2 is just pi. So A0 is pi. Well, AN is equal to this integral, but since this is an even function, we can reduce this to integral over one part, only the positive part, and multiply this by 2, of course. Okay, so integral over the positive half interval is easy to compute. The method is still to use integration by parts. Okay, you should use integration by parts to find the antiderivative of this function. So anyway, you will find this result exactly as in the previous question. Okay, so Bn would be 0 because this is an even function, no Bn. So this is the Fourier series for the even function, absolute value of t. This is the constant part. It comes here. So A0 is divided by 2. While An is not divided by 2. Remember this. A0 is divided by 2, but An is not divided by 2. Okay, so let's move on. So we know that computing the Fourier series of odd function or even function can be simplified, right? As shown in the previous pages. Actually, for any odd function defined on the half interval, we can, for any function defined on the half interval, we can extend it to be odd function, okay? Provided it satisfies this condition. So we can extend it to be odd function in this way. We define on the negative half of the interval the function to be this value. So if t is negative, then negative t is positive. Well, when negative t is positive, f of this number is known because f is already defined on the positive half of the interval. So when negative t is positive, so f of negative t is well defined. So you can define f of t when t is smaller than 0 in this way. So this extends the function to the whole interval, including the negative half of the interval. After such an extension, you would get odd function. Okay? Because you have a negative sign, you would have an odd function on the whole interval. And this odd function can be represented by sine series, right? Series of sine functions. So what does this mean? This means that any function originally defined on the half interval can be represented by a series of sine functions. Okay? Because any function can be extended to be an odd function. Therefore, any function on half interval can be represented by sine function. And similarly, you can also extend a function in an even way. Okay, you can make such extension as this without the negative sign. If you compare this with this negative sign, you would extend it as the old function. Without this negative sign, the new function, the extended function, would be an even function, right? So you can extend the function to be either an old function or even function like this. So if it is extended as an even function, then it can be represented by series of cosine functions. So anyway, so any function initially defined on the half interval can be represented by a series of cosine functions because you can regard it to be extended to an even function. Okay. So we will only say that the function is a function defined when t is between 0 and pi. Okay, we do not need its definition for when t is smaller than 0. We only need it to be defined on the positive half of the interval. If this function is defined on the positive half of the interval, then we can represent it as sine series or cosine series as we wish. So now let's express this function as a sine series. Okay. So we need to first modify the definition of this function a little because this function does not satisfy a condition. So f0 is not equal to 0. f0 is also equal to 1. Okay. So if it does not satisfy this condition, then we cannot define it as a complete odd function because f0 should be 0 for odd function. So we can modify the definition. Let's consider f tilde, which is a modified function. We only modify the function value when t equals 0 or pi. So when t equals 0 pi, we modify it as 0. For other numbers, for other t, we still define this the same as the original function. It's the same as the original function. It's 1. Only modified when t equals 0 or pi. Okay, so this new function can be extended as an old function. And the Fourier coefficient for the old function is this. So there is only Bn, right? An would be always 0 for old function. So we don't need to compute An, it's always 0. So Bn is this. And what is your f tilde? The function is equal to 1, actually. When you compute the integral, when t is between 0 and pi, the function is equal to 1. Okay. So you are actually computing integral of the sine nt. So it's easy to find the integral. It's this. So what you have is that the modified function is equal to Bn times sine nt, then sum up all the n. There are infinitely many terms. So the constant number 1 can actually be represented as a series of sine functions. Okay. So this series of sine functions is always equal to 1 when t is between 0 and pi. When t is 0 or pi, of course, it equals 0. Okay. So what you get is that when t is strictly between 0 and pi, actually this series is always equal to 1. So let's have 5 minutes break. Let's consider the next example for piecewisely defined function. So this function is defined piecewisely with two different expressions. So when t is smaller than half pi, ft is 0. When t is bigger than half pi, the function is 1. Okay, so it has two different expressions. We want to find the Fourier sine series of this function. It means that to represent the function by a series of only sine functions. Okay, so this is a function defined initially only on half interval between 0 and pi. You see, t is between 0 and pi here. Okay. There is no definition of the function when t is smaller than 0. Initially, the function is defined only on the half interval, but when we want to find its Fourier sine series, actually equivalently, we extend it to be odd function in the interval. Okay, so when we extend it to be an odd function, we need to redefine the function at 0 and pi. Okay, so we define f0 to be 0, always for odd function. We define f pi to be 0 always. So we need to modify the definition of the function because initially the function is not equal to 0 when t equals pi. So we first modify the function by redefining f pi to be 0. Then the function can have an odd function extension. Okay. For the extended odd function, the Fourier coefficient would be this. Okay. While you notify that the function is defined piecewisely, right? You can split this integral into two parts. On the first part of the interval, okay, the function is just 0, so that part would be 0. Okay. On the second part of the interval, so when t is bigger than half pi, the function equals 1. So for this part, you have 1 times sine nt. You need to integrate this sine nt over this interval, smaller interval. Then you would get this result. So this would be your Bn, and finally, the Fourier sine series of this function would be Bn times sine nt with all infinitely many n. Okay. So that's a Fourier sine series. You can similarly find the Fourier cosine series of a function initially defined only on the half interval. So for example, let's consider 1. So what's the Fourier cosine series of this constant? Actually, you want to express 1 as a Fourier cosine series with constant part, right? So it's easy to see that A0, if A0 is 2 over 2, you get 1. If AN is 0, all the rest part would be 0. So you get 1 plus 0 equals 1, right? So that would be the Fourier cosine series of this constant. Okay. So A0 is 2, AN is 0. Then right side give you 1 equals left side. Okay. So Fourier cosine series of a constant is just the constant itself. Let's compute the Fourier cosine series of this function, fft equals t, when t is between 0 and pi. Okay. According to the formula, the Fourier coefficients is an. An would be equal to the integral over half interval. So from 0 to pi. Okay. Multiply this by additional 2. Okay. So you would get a pi. And for an, you should consider the integral of t times cosine nt, again over the half interval from 0 to pi, and then multiply the result by additional 2. So I already show you how to find the antiderivative of this function t times cosine t. Okay, you should use integration by parts to find the antiderivative. Okay. So anyway, in the end, you get a0 and an. You should substitute this a0 here and an here. This would be the Fourier cosine series of t. There is no sine function, right? Because we only consider cosine series. That's equivalent to the Fourier series of the even function extension of this function. Okay, you can first extend this function to be an even function, and then for that even function, its Fourier series would consist of only cosine functions. It would be this. Okay, you can compare the result with the Fourier cosine series, with the Fourier series of absolute value of t. Okay. I leave this as an exercise for you to compare this after class. For functions piecewise defined, you can also find its Fourier cosine series. Okay, we considered this function before for its Fourier sine series. Now let's compute its Fourier cosine series. For Fourier cosine series, a0 is defined as this integral times 2. Okay, but the function is equal to 0 when t is smaller than half pi. So actually, the integral is only non-zero when t is bigger than half pi. When t bigger than half pi, the function equals 1. So you get pi minus half pi is half pi. So pi minus half pi times this 2 over pi. So you would get 1. Well, this is only a0. For an, you should multiply ft by cosine nt. So again, f of t equals 0 when t is smaller than half pi. So you don't have the other part. Okay, when t is smaller than half pi on this part of the integral, function is always equal to 0. So the integral of 0 is 0. So you don't have this part. What you have is only the integral from half pi to positive pi. And when t is bigger than half pi, f of t is equal to 1, so you get 1 times cosine nt. So you can find the antiderivative of cosine nt, right? It's just the sine nt over n. You get sine nt over n here. Well, so this is your an. You can substitute the an into your formula to construct a Fourier cosine series. This is your an. This is your a0 is 1. a0 over 2 here. Okay. So what is the sine n pi over 2? You can see that if n is an even number, this would be 0, right? If n is even number, half n would be integer. Sine integer times pi would be always 0. So n cannot be an even number. So for all even n, this would be 0. Okay. For odd n, this is not 0. This would depend on the sign of n actually. If you substitute n to be odd number, 2n minus 1, you get 2n minus 1 here. Then this sine function would be equal to minus 1 to power n. Okay, this n is replaced by 2n minus 1. Okay. These are odd numbers. You don't have even number because when n is even number here, you get 0. So there are only odd terms left. So this is the Fourier cosine series for this discontinuous function. You see that for the same function, you can find its Fourier cosine series or Fourier sine series. They are different, both equal to the original function. Well, this is slightly different from the previous question. Again, this is piecewisely defined. It's still 0 when t is smaller than half pi, but it becomes t minus 1 here. Okay? It's a little different from the previous question in that there is additional minus 1. If you consider the previous question, there is only t here, but here t becomes t minus 1. Okay? There is only a little difference, actually. So if you define the function g of t to be the piecewisely defined function consisting of 0, 1 defined on each piece, while you define h of t to be this function consisting of 0 and t defined on each piece. So h of t is the function in the previous question, this function. We call this function h of t in this example. Well, g of t is just this function. We consider this g of t also in the previous example. If you see that we consider this function here. The Fourier cosine series of this function is already computed. It's just this series. Okay, so we know Fourier cosine series of this function. We also know Fourier cosine series of this function. So we can use the Fourier cosine series of the two functions to construct the Fourier cosine series of the new function. Okay, because for g of t and h of t, we already know the Fourier series, cosine series. Well, our new function is just equal to h minus g, right? Okay, h of t minus g of t will give us f of t here. So you already know h of t and g of t. You substitute these two expressions, okay? You can get the expression for f of t. So by this way, you don't need to compute the Fourier coefficients again. You don't need to compute integral of f of t times cosine functions. Again, you just use the previous two results. You combine the two results, you can get Fourier cosine function of the new function. Okay. So far you should already be familiar with how to compute the Fourier coefficients of a given function, how to write down the Fourier series of a given function. And you should know that the Fourier series you write down for a given function is actually equal to the function, normally, at least when the function is continuous. Okay. So the Fourier series actually equals the function when the function is continuous at t. But sometimes they are not equal. For example, when the function is discontinuous. In this case, the Fourier series would give you the average value from the left side and the right side. If the function is discontinuous at t, then if it has left value and a right value, Fourier series simply equals the average value. Okay. And of course, when t equals negative pi and positive pi, okay, the function is considered to be discontinuous. And the Fourier series at this point, when p equals negative pi and positive pi, is always equal to the average value. Let's consider this example. We already found the Fourier series in the previous question. Okay, this is the Fourier series of absolute value of t. We already found it in the previous example, so we directly use this result. We know that absolute value of t is continuous at the whole interval, so it's always continuous. So this equality always holds for arbitrary t. When t equals, when t is from negative pi to positive pi, this equality holds. Okay. So you can substitute some special value of t to get some beautiful identity. For example, For example, let's substitute t to be 0. If we set t to be 0 in the identity, left side is 0. Right side, you get cosine 0. Cosine 0 is just 1. So what you get is this series. Well, you can multiply both sides by pi. You can multiplying this by pi, you can eliminate the pi in the denominator. Eliminate this pi. Then you get a pi square over 2. You can divide both sides by 4. You get pi square over 8. So you get pi square over 8. But the left numbers will be square of odd numbers. Okay, n starts from 1. So you get 1 square here, or 3 squares, 5 squares, 7 squares. These are all the squares of odd numbers. Okay. So the sum of all these numbers give you pi square over 8. You see that this is an identity that relates odd integers to pi. There is a natural relation between integers and pi. This is found by using Fourier series. Okay. So Fourier series can give you a lot of such interesting identities relating numbers that are seemingly different, seemingly not related. Okay. So how is pi related to odd integers? It's not obvious at all, but the Fourier series give you this identity. Okay. You can substitute the special value of t to get a different identity. For example, you can find the Fourier series of t squared. Okay, the Fourier series of t squared would be the right side. You can check this by yourself. And t squared is an even function. Okay. The Fourier series is equal to t squared. What does this mean? You can substitute t to be 0 again into the expression. So when t equals 0, left side equals 0. Right side, again, cosine 0 is 1. So you get this. Okay. What does this mean? You divide 4 on both sides, you get pi squared over 3 times 4. You get pi squared over 12, actually. While this term is here, if you write it down, write the first few terms, you get 1 minus 1 over 2 squared plus 1 over 3 squared. So it's an alternating series. The sign is alternating. Minus positive, minus positive, minus positive. Okay. Well, this series is equal to pi squared over 12. It's still pi squared divided by different integer. Okay. You see that this is, if you look at the odd terms in the series, you get 1 plus 3 squared here, 5 squared here, 7 squared here. It's actually the same series in the previous question. See? The previous question, this equals pi squared over 8, but in the current question, if you add the even terms, 1 over 2 squared, 1 over 4 squared, if we add the even terms, it becomes pi squared over 12. Okay. So what we get is that if you consider the odd terms, you get pi squared over 8. If you add the even terms, the blue part is just the above series. Okay, then you get pi squared over 12. Well, you can consider the difference between the two series. If you consider difference, you would get the first series minus the second series, give you this identity consisting of all the even terms. Okay, 2 squared, 4 squared, and 6 squared. Okay. Well, this would be equal to pi squared over 8 minus pi squared over 12. It's pi squared over 24. Okay. Well, you can extract all the even terms, all the 2 squared from the even terms, because every term contains 2 squared. Right? The 4 squared is just a 2 squared times 2 squared. 6 squared is just a 2 squared times 3 squared. This equals 2 times 4. 2 times 5 with squares. Okay. Well, you can multiply both sides by 2 squared. So this first term will become 1. Second term will become 2 squared, 3 squared, 4 squared. You multiply both sides by 2 squared. So you get pi squared over 6 on the right side. So this consists of all the integers. The sum consists of all the integer squares here, give you pi squared over 6. But if you consider odd integers, you get pi squared over 8, slightly smaller. Okay. These are interesting identities that you found by using Fourier series. Okay. Without Fourier series, it's difficult to find this result. Okay. Very interesting, relating integers to pi. There are many more interesting identities that you can find by using Fourier series. Okay. You can look at the exercise questions. Okay. So in this lecture, we introduced how to calculate the Fourier series of a given periodic function with period 2 pi. Okay, the function is always defined from negative pi to positive pi. We also introduced Fourier sine series and Fourier cosine series. Okay. A Fourier sine series is for odd function. Fourier cosine series is for even function. Okay. And if you find the Fourier series, you can substitute some special value of t into the Fourier series. Then you can find very special series, very special identities. Okay. There are many exercise questions in this lecture, and I hope that you can try all of them by yourself. So since tomorrow is a public holiday, we don't have tutorial for exercise questions of this lecture. Okay, but I already uploaded this all the brief solutions to these questions to the Blackboard system. In the lecture notes, you would see the brief solution. When you work out this by yourself, you can compare your solution with this solution to see whether you are correct. Okay. So there will be no tutorial for this lecture. Hope that you can finish this by yourself. And also there is assignment uploaded in the Blackboard system. I hope that you can have a look at the deadline of assignment in the Blackboard system and submit assignment before the deadline. Submit a single PDF file. Okay. Don't submit a lot of pictures. Just submit a single PDF file. Try to make a single PDF file from the pictures you have. Okay. You can take photos by your cell phone or scan your with the machine. So. But please upload a single PDF. Okay. So now, hope that you enjoy today's lecture. And if you have any question, you can stay and ask or send me emails. I hope that everyone can have a good New Year. Page 23. So this is page 23. Do you have any questions? Okay. So we find the Fourier series, right? So this is Bn, we have with this expression. So Bn times sine function is just a Fourier series of this function. Okay. As the Fourier series of this function, it equals this function when t is continuous. For example, when t is between 0 and half pi, the function is continuous, but it's discontinuous when t is not equal to, when t is equal to half pi, the function is discontinuous because its left value would be 0, right value would be 1. Okay. When t equals half pi, the series would give you average value, would give you half actually. So this I didn't write here because we learned this later. So here, when t is bigger than half pi, the function is again continuous, it's just a constant. But t cannot be pi because when t equals pi, we already changed the definition, f pi equals 0. So this series would be equal to 0 when t equals pi. Okay, I should write here. The reason that we require f0 to be 0 because we require it to be an odd function. Okay? Only odd function has Fourier sine series. So if a function is odd function, then f0 is equal to minus f minus 0. Right? And this would give you this result. So for odd function, the function value should always be 0. So f0 should always be 0. Otherwise, it cannot be odd function. So this is one condition we require. We require this condition so that the function can be odd function. But we also require f pi to be 0. Otherwise, the function cannot be odd function. Okay. Otherwise, the function is discontinuous at pi. So for 2 pi periodic function, we require the function to be periodic, like here. So if f pi equals f minus pi, then the function is periodic, you see. Because when you reach pi, you can return from the left side. So the function is periodic and continuous. You should regard pi and the negative pi to be a single point. They coincide actually, so that when you go to the right side, you return from the left side. So this is periodic function. But if f pi is not equal to f minus pi, then the function would be not continuous at this point. In that case, the series would converge to average value. Okay. Just like half pi, it converts to average value. Any other questions? You are welcome to ask questions. Okay. So if there is no more question, so then let's see you next week. Happy New Year. But I remember that next week doesn't have class.